Hi everyone, today we're going to be talking about topic 8.8, properties of buffers. I mentioned buffers I talked about buffers very briefly in topic 8.4, but a buffer is a mixture of conjugate acid-base pair that resists large changes in pH. Now, by conjugate acid-base pair, I essentially mean you mix together, if I'm going to take, for example, acetic acid, that's HC2H3O2, and I mix that with its conjugate base. Right, this is the weak acid, this is the conjugate base. If I mix these together, that's the conjugate acid-base pair. They require more than 10 to the minus third molar concentration of both species. In other words, they need more than 10 to the minus 3 molar weak acid and conjugate base, or weak base and conjugate acid. Concentrations must be roughly equal. And there's a whole bunch of different systems that use buffers. One is our blood. Right, we don't want our blood suddenly becoming super acidic or super basic, and so our blood is a buffer solution. So that way, if you eat something that's really, really acidic and that gets into your bloodstream, it's not going to completely ruin your bloodstream. Pools are another one. We typically add things to pools in order to make sure that the acidity of the pool stays relatively the same, or the basicity of the pool stays relatively the same. And so you typically use buffers in a situation where you don't want your pH changing a whole bunch. So there's two ways that we typically make a buffer, and it's pretty simple, all things considered. Basically just mix a weak acid. I'm going to take acetic acid as my example, HC2H3O2, and the salt, any salt of its conjugate base. And so I can take, for example, NaC2H3O2. Right, this is basically just a source of the conjugate base, which is C2H3O2 minus. And so any salt of that conjugate base, or if you're looking at it from the weak base standpoint, you can mix a weak base like NH3, for example, with a salt of its conjugate acid, for example, NH4Cl. Right, and so if I mix NH3 with NH4Cl, I make a buffer, or if I mix HC2H3O2 with NaC2H3O2, that makes a buffer solution. The second way to do it is to add strong acid and just partially neutralize the weak base, or add strong base and partially neutralize the weak acid. And so essentially, if I'm going to think of a titration curve, I can basically stop here, right, at a point where I have, where it's partially neutralized, not completely neutralized. And so this is kind of how a buffer works. We have this example here, this CH3COOH. This is just another way of writing C2H3O2. H2C3. HC2H3O2. And this here is just another way of writing C2H3O2 minus. And so it's acetic acid reacting with water. If you mix a little bit of the acid with a little bit of its conjugate base. If I add H3O plus, you'll see that the concentration of the weak acid will increase. The conjugate base goes down a little bit, but not by that much. And the exact opposite is true is if I add OH minus. The conjugate base will go up, and the weak acid will go down, but the change is minimal. And so it's going to resist changes in pH as a result of that. Now, in the next two slides, I want to show you mathematically the fact that this is true by using a Rice table and thinking about the equilibrium. So let's look at this example. I'm going to read it carefully to get all the information that we need. So it says, consider a buffer that has 2 moles of acetic acid, which is this right here. Another way of writing it is HC2H3O2. They're the same thing. And 2 moles of sodium acetate. And so it's just the conjugate base of acetic acid mixed with made from mixing it with sodium hydroxide. I have 2 moles of that, and they're both dissolved in 1 liter of water. And so I essentially have 2 molar HC2H3O2, and I have 2 molar C2H3O2 minus. So the same concentration. So it says if I add 0.1 liters of 0.1 molar sodium hydroxide, which is a strong base, to the buffer system, it will react with the acetic acid to form the conjugate base shown below. And so essentially we have this reaction, the acid mixed with OH minus to make conjugate base and water. Now if you notice, these two are already present in solution. And so another way to think about this, if we think back to Unit 7, is that this is similar to the common ion effect. And so in the next slide, I'll kind of show you what this looks like in terms of a Rice table. And so let's just keep all this information in mind. 2 molar each of these, and we have 0.1 molar of 0.1 liters of 0.1 molar NaOH. So let's make our Rice table. The reaction here, which we're already given, is HC2H3O2 plus, I've added NaOH to it, so that's OH minus. It makes the conjugate base, which is C2H3O2 minus, and water. So that's the reaction. And now I'm going to do the rest of the Rice table actually in terms of number of moles rather than concentration. And so I have 2 moles of acetic acid. I have 0.010 moles of OH minus. I have 2 moles of acetate anion, and because water is liquid, we don't consider it in the reaction. Change. Well, I know that I've added this much moles of sodium hydroxide. That's going to react with my acetic acid, and so it's minus 0.010 moles. Minus 0.010 moles, because I've used up all my sodium hydroxide. And on the right side of the reaction, I've added 0.01 moles. If I add this together, I get 1.99 moles here, 0 moles of sodium hydroxide, and 2.01 moles of acetate ion. And so what you'll notice here is that these two numbers are basically the same. And so because I already have some acetate ion in there, I don't really change my concentration of each of them that much, and so the pH won't actually change by that big of a factor. That's essentially how a buffer works. If you notice when you do the Rice table, you get a really, really small change in either one of the ions, even though I added a good amount of base to it. And so that's just an example of how these buffers work in reality. We'll spend some time in class going over more of these problems, but for now, that's all. Thanks, guys.